Hi, my name is Brad Frieden. I'm an engineer at Agilent Technologies. Been involved in digital design techniques with logic analysis for about the last 10 years. And I'd like to take some time today to talk about an application called Reconfigurable radar and how teams are having to deal with the debug and validation of such systems. What you find in a reconfigurable radar, since part of that design includes FPGAs with digital signals, generally dealing with an IQ vector modulator, and stages that are analog and RF out to the antenna, I have very different teams of people trying to work together. FPGA designers familiar with their tools, RF designers and their tools. And what we're finding is a signal out on the antenna not looking right. Now you've got some controversy about where is the root of the problem. The RF guys may be saying, I think you guys have a problem with your digital filtering. The digital guys are wondering, have you got some compression going on in your output amplifier? You got to sort that out. That's what we're going to spend some time looking at today. I'd like to take just a minute to show you the measurement setup here. On the left side we have a 16800 series logic analyzer. That's probing down onto our system with flying leads and picking off those digital signals. And it has the 89600 VSA software running on its Windows system. On the right side we've got a 9000 series oscilloscope. It's probing analog signals from the D to A converter into a coaxial input, and it's also running the 89600 VSA software. Let's take a look at the block diagram of our system today. This is what you would find in really most any typical reconfigurable radar system. A front end that's digital, the radar digital processor. That consists of an FPGA. Then I have your classic components in the RF section bringing signals out through a power amp finally to an antenna on the transmit path. And similar on the receive, RF microwave back to the digital side of things. And where we're going to really focus today and where our target system that we have here is focused is this digital section that then drives out analog IF that gets upconverted to RF. If we dive deeper into that radar system block on the digital section, what we find is that that is a IQ vector modulator circuit. I have I and Q data, it gets upsampled, root raised cosine filtered, so I have filtered I and Q, and then that gets digitally upconverted to digital IF, and that drives a D to A converter and on out to your RF sections. This design, which ends up being targeted into an FPGA, was created in a tool called System View. And this is a view of what that looks like after that high-level description and the creation of the design. This can be targeted by taking hardware description language that it creates, like Verilog or VHDL, and you can bring that down into an FPGA, as we've done here, and it will take measurements on. Now what's important is I can take this design and I can create a simulation of the signals that would be present and drive those into this 89600 VSA software. When I do that, I form really a golden standard. I can see what the spectral width of this transmit signal at the digital level within the FPGA should look like. I can see how the frequency should be shifting linearly. This is a linear frequency modulation radar. And there is a specification there that I must meet. And I can see the classic view of the real part of the I signal. And finally, what that amplitude looks like of these pulses of radar across the width of the pulse. These are what I'm going to need to be at least as good as with the signals, the real signals, both at the digital level and then out at the analog RF level. And that's what we're going to look at now with our test equipment. So let's consider this situation where things just really aren't looking right out at the transmitter antenna. And the digital team is having to defend themselves that, hey, we didn't make a mistake in filter coefficients of those digital filters. How are they going to do that? Well, one way is to probe right into that FPGA at the point where those filtered IQ signals exist, measure them, and feed them into that common 89600 VSA environment. We want to compare to this golden standard. So let's do that. If we look at the logic analyzer, we're running a tool called the FPGA dynamic probe. This lets us look at different points within the FPGA. For example, bank 0 is this DAC input signal, this digital IF. So we're going to choose that bank, and when I click OK, a multiplexer inside that FPGA is selecting those exact signals and feeding them to pins that I'm probing with flying leads. So I'm going to press Run, and what we'll end up seeing, part of it is a hexadecimal view of these signals, which are pretty hard to understand. But if I view it as a chart, that's where I can now see this pulsed radar signal. That's a digital signal, but then represented in a chart mode. With this, I can import that into the 89600 VSA to look at the details. So let's do that. If we go to VSA and bring up a display where I can view things like the spectral width and how the frequency is changing across the pulse, the very things we looked at in that golden standard. And within the menu, I say Input Digital, and I can select that I want the inputs to come from the logic analyzer. I can pull into it the bus, this DAC input bus that I care about, and tell it that it's real and it's offset binary base. Well, I'm ready to go. And if I hit this Run button, I'm going to take an acquisition of these signals, of the filtered, in this case, this digital IF signal, and I'm going to pull it into VSA and let it process it. So here we go. And I'll pause it here when we get to the center. There's that spectral width, exactly what we were looking for. I can see the frequency changing linearly across the pulse, exactly as was simulated from that high-level design. I can see the amplitude of the pulse across the pulse, and there's that classic real part of the eye. These digital designers have proven that through this digital part of the design in the FPGA, they've done their job. They do not have any question now that the problem is theirs. The RF team is going to have to go look on their side. So the next stage of this design is getting out of the digital and through the D to A converter into analog IF. So the next logical place to look is coming out of this design, analog, and looking at it on the oscilloscope. Here we see that chirp radar signal. Again, a bit like the logic analyzer. I can't really make a lot of judgment about this thing until I do some more processing on it. And that's where the VSA software will, the 89600 VSA software will help us. So we will bring up the VSA and import this scope signal. So I'm going to hit Run. And there we see proper spectral width, change of frequency across the width of the pulse, these pulses that are coming in, and that classic I signal, as well as the amplitude. So we've shown the digital part of this IQ vector modulation path, perfect. Passing through the D to A converter, no problem at all. The problem must be further out once I upconvert the analog IF into these RF stages and out through the amplifier. That's where the final work will happen. So we've seen how in a reconfigurable radar design, where I have this combination of the digital domain and analog RF domain, there are some ways to merge these different worlds together, and that is that 89600 VSA software. First, with digital signals input to it. Second, with analog or RF signals input to it, to create that common analysis environment where I raise my level of abstraction so I can see in a glance, am I chirping that radar properly in frequency, for example. And this greatly speeds that process of narrowing down where the problem might be. So if this is of interest to you, please see the website below, and thanks for watching.